Hey there. You know how we love to dig into those unexpected nuggets of knowledge in the data world? Well, we got sent this paper, and it's a fascinating look at how those good old-fashioned machine learning models, the ones we sometimes think of as, simpler, they're actually outperforming those flashy deep learning algorithms. Can you believe that?
And what's really interesting is that it's not just any data, it's tabular data. The kind of stuff we see in spreadsheets and databases day in and day out. Rows and columns, the foundation of so much data analysis.
It's true. And it really makes you think twice, right?
Mm.
Because there's this assumption that deep learning can solve everything, be the best at everything. So what's the deal here? Why are these tree-based models like XGBoost, Random Forests, why are they still holding their own, especially when it comes to tabular data?
Well, these researchers, they really wanted to get to the bottom of it. They put together this incredibly comprehensive benchmark, testing a whole bunch of different deep learning models. I mean, we're talking MLPs, ResNets, transformers, everything you can think of. And they pitted them against these tree-based models on a massive data set.
How massive are we
We're
talking?
talking 45 data sets. And they span a whole range of different fields. So this wasn't just some fluke or a niche observation. It was a pretty broad look at the landscape.
45 data sets, that's impressive. So
Yeah.
they weren't messing around. But what did they actually find? Did these tree-based models live up to the hype?
They really did. And it wasn't even close in a lot of cases. The interesting thing is that even after they really fine-tuned and optimized the deep learning models, gave them every advantage they could, those tree-based models just consistently came out on top, especially when they were dealing with data sets that were in the 10,000 sample range, which is, a pretty common size for a lot of real-world applications. So it's not just some theoretical thing.
Right, this is really getting down to the nitty-gritty of how we use data every day. So, okay, we've established that this isn't just some random occurrence. Tree-based models are clearly doing something right. But the million-dollar question is why? Why are they so darn good at handling this tabular data? And that's where this paper really digs deep. They actually identify three main reasons, or as they call them inductive biases. And I love that phrase because it gets to the heart of how these models think.
Yeah, inductive biases, it's a mouthful, but it's important. And the first one that really clicked with me is how real world data, well, it's messy. It's full of inconsistencies, bumps and curves along the way. It's not always this pristine, perfectly organized set of information.
It's like expecting a race car to, navigate a dirt road full of potholes. It's just not what it was designed for.
Yes. Perfect analogy. You need something that's a bit more robust, right? Something that can handle the bumps, like a good sturdy Jeep. And that's essentially what a tree-based model is in this scenario. They're built for that kind of unpredictable terrain. Deep learning models, on the other hand, they tend to prefer things to be, well, a bit more predictable, smooth, like a well-maintained racetrack.
So what you're saying is that in the real world, where data is messy and full of surprises, sometimes it's those simpler, more adaptable models that really shine. That maybe it's not always about chasing after the shiniest, newest algorithm.
Exactly. And the researchers actually illustrate this point beautifully in the paper. They use a data set about electricity consumption, and you can visually see how the tree-based model is able to gracefully navigate all the peaks and valleys in the data, whereas the deep learning models, they kind of get thrown off a bit. They're not as adept at handling those sudden shifts and changes.
Fascinating. So inductive bias, number one, tree-based models. They're the ultimate off-roaders of the data world. What about the second reason they're so good? What's their next superpower?
Okay, this one is all about irrelevant information. Think about it. You've got a spreadsheet, it's got tons of columns, tons of variables. But the thing is, not all of them are actually useful for what you're trying to do. Some of them are just noise, they add complexity without adding value.
Like having a GPS that's trying to give you directions, but it's picking up signals from 5 states over. It's not exactly helpful.
Exactly. And as it turns out, deep learning models, especially those MLPs, they can be really sensitive to this irrelevant information. Their performance takes a hit because they're trying to make sense of data that doesn't really matter, and it slows them down.
So they're getting bogged down in the weeds, so to speak. Whereas tree-based models are a bit more discerning. They know how to filter out those distractions.
That's exactly it. The researchers actually tested this by adding and then removing irrelevant features from the datasets, and guess what? When they removed the irrelevant information, the performance of the deep learning models, it shot up. But for the tree-based models, it didn't make as big of a difference because they were already doing a pretty good job of ignoring that noise in the first place.
Okay, so we've got tree-based models conquering messy data. They're masters at ignoring distractions. What's the third advantage they've got up their sleeve?
Well, this one's a bit tricky to explain, but it's all about how tabular data, it has this kind of inherent order, a structure that actually means something.
Okay, now you've got me curious. How does structure play into all of this?
All right, so imagine you've got a spreadsheet, right? And it's got information about, let's say, your customers. You've got a column for their age, their location, maybe what they bought, how much they spent. That specific order, the way those columns are arranged, it makes sense, doesn't it?
Yeah, absolutely. I mean, if you started scrambling those columns, it would be total chaos. You'd lose all the relationships between the data points.
Exactly. And this is where deep learning models, especially those MLPs we talked about, they have this kind of quirk. They operate under something called rotation invariance.
Rotation invariance. Sounds like we're about to do some statistical gymnastics. What exactly does that mean?
Essentially, it means that if you were to rearrange the columns in your data, like if you were to rotate it, their performance, ideally, it shouldn't change. That they're designed to be flexible, to find patterns no matter what order the information is in.
Well, at first glance, that sounds like a good thing, right? Like they're saying, hey, throw anything at me, I can handle it.
You'd think so, right? But here's the thing. Because they're not paying attention to that inherent order of tabular data, they kind of miss out on those crucial relationships we were just talking about. It's like they're reading each word in a sentence, but not really understanding the grammar, the syntax that gives it meaning.
So it's like they're missing the forest for the trees, or maybe the spreadsheet for the cells in this case. They're so focused on those individual pieces of data that they miss the bigger picture, the one that's embedded in the structure itself.
Exactly. And to really drive this point home, the researchers, they did something pretty clever. They actually scrambled the data. Like they just threw the columns into a completely random order. And guess what happened? The performance of those deep learning models, especially the MLPs, it tanked. They just couldn't adapt because that inherent structure, that natural order, it was gone.
Wow, that's really interesting. So it's like these deep learning models, they're missing a key piece of the puzzle here, that understanding of context, of relationships, that's so fundamental to the way we as humans organize information.
Exactly. But tree-based models, they don't have that same limitation. They're considering the features both individually and in relation to each other, so they're not as affected by this whole rotation thing. They're still able to pick out those important signals, even when the order is all jumbled up.
So they're kind of more intuitive, more in tune with how we naturally think about and organize information.
That's a great way to put it. They're able to work with the data as it is, respecting that inherent structure, which gives them a real edge.
Okay, so let's do a quick recap here. We've got tree-based models. They're handling messy data, like champs. They're ignoring irrelevant information, like pros. And they're respecting the natural order of things. It's like they've got this deeper understanding of the game.
And this is where it gets even more interesting. Because the researchers, they don't just stop at highlighting these strengths of tree-based models. They go a step further and they pose this really intriguing question.
So if these tree-based models are so good at naturally getting tabular data, kind of seeing the patterns that maybe deep learning misses, it makes you wonder if we can actually, teach deep learning to be better at this.
Right. Like, can we take what we've learned about how these tree-based models work so well and actually build that into how we design deep learning models, especially for this kind of data?
It's like saying, hey, deep learning, you got a lot of potential, but you might want to take a page out of the tree-based playbook if you really want to dominate this whole tabular data world.
Yeah, exactly. And there's actually some really cool research already happening in this area. Imagine a deep learning model that can adjust its own structure on the fly, depending on how messy the data is. Or one that can learn to just ignore those irrelevant features, be a bit more selective about what it pays attention to.
It's almost like we're giving these deep learning models a crash course in those key inductive biases we were talking about earlier, teaching them to embrace the chaos in a way.
Exactly. And think about what we could do if we could actually combine that adaptability, that intuition of tree-based models with the sheer power and scalability of deep learning. I mean, we could potentially see this whole new generation of models that are not only incredibly accurate, but also way more transparent and interpretable.
It's like not only are they performing better,
Mm-hmm.
but we can actually understand why they're making the decisions they're making. That's a game changer.
It really is,
Yeah.
and it highlights something really important about this whole research paper. It's not just about, crowning a winner in some machine learning competition. It's about pushing the boundaries of what we know, constantly questioning, refining the tools we have so we can actually solve real-world problems in a more meaningful way.
Absolutely. And it's a great reminder that the field is always changing, always evolving. Just when we think we've got it all figured out, something like this comes along and opens up these whole new avenues for exploration.
Exactly. This paper has really sparked a conversation, a challenge to rethink how we approach tabular data. And who knows what incredible discoveries might come out of that.
I love that. So for you, our listener, we'll leave you with this.
Yeah.
Don't be afraid to challenge assumptions, to think outside the box. Just because something is new or trendy doesn't always mean it's the best solution. Sometimes those tried and true methods, they still have a lot to offer. And hey, maybe you'll be the one to bridge that gap, to design those next-gen models that take the best of both worlds and really push the boundaries of what's possible. Until next time.